Our topic for today is going to be integer partitions. So typically we talk about integer partitions of n. So we're going to let n be a positive number. And we're going to be looking at the sequences lambda 1 plus lambda 2 plus lambda k equal to n, where each lambda I is greater than or equal to 1. So this is what we call an integer partition, and we want to count these. And we don't care about the order. So we think of these as a multiset of lambda 1 up to lambda k. A multiset because, of course, we can repeat a number, but since we don't care about the order, we might as well write them in a canonical order where we take the biggest part first and then the next biggest and so on down to the last. So by taking them in weakly decreasing order, we can always make sure that we don't write the same thing twice. So if we want to think, for example, about, let's say, the partitions lambda that are partitions of 4. So this means that the sum over all I of lambda I needs to equal 4. In general, we'll have it equal n, but here we can have it equal to 4. So we can think about how many ways can we write this. Well, let's think about starting with the biggest number. So we've got a 4. So we could just write 4. Okay, what else could we do? Well, if we don't start with a 4, we could start with a 3. And then we could have a 1. That's certainly a reasonable way to do it. And those add up to 4. Okay, what else could we do? Well, we could start with the number 2. And then we could have another 2. So 2 plus 2 is 4. How else could we do it? Well, starting with 2 again, we could have the next 2 parts be 1s. We can do it this way. 1, 1. Oh, maybe try to be a little more consistent here. Or we could have all the parts be 1. And that's it. Those are the 5 integer partitions of 4. Okay, so we have, this one has, we say 1 part. These have 2 parts, this has 3 parts, and this has 4 parts. So we see each lambda I is a part of lambda. And in this way, we can be systematic about doing it. So there's actually no closed formula for the number of integer partitions of n. So we're going to let that be denoted by p of n. This is going to be the number of integer partitions of n, which is the number of these sequences that add up to n. So again, there's no closed formula for it, but we want to be able to count it. We want to be able to come up with some way to compute these numbers. And we can do that by being systematic in how we generate them and thinking about it in terms of a generating function. So I want to think about the formula p of x, which is going to be our standard generating function, the sum from n greater than or equal to 0 if you like, 1 if you prefer. Maybe we'll make it 1. Of p of n, x to the n. And we want to say, okay, what does this look like? Can we come up with a closed formula for the generating function? Just because we can't do it for the numbers themselves doesn't mean that we can't do it for the generating function. So the right way to think about this is to think about how one could build a partition. So here when we were doing this example, we thought about, okay, well, we can take maybe a board, which is going to be where we're going to keep track of our partitions, and we could think about taking some number of 4s. So maybe I have 2 4s. Okay, and then we could think about, okay, well, I could take some 3s as well. Maybe I have a 3. And then we could think about taking some 2s. Maybe we'll have 3 2s. And then we could take maybe some 1s. And maybe we'll give ourselves a 1. So this is a perfectly good integer partition, and we can add up the number of bips to see how much it adds up to. But if we think about how we made these choices and how we came about constructing this partition, that'll give us the clue we need in order to write down the generating function. So if we think about what are the choices that we have when we're coming up with a partition of n. So here, it's the coefficient of x to the n that we care about. But let's just think about making any partition and not caring about how big it is at first. And when we do that, we can say, okay, well, what's our sort of smallest part? How many 1s are we going to have? Each one contributes, if we have 0 1, or we could have 1 1, or we could have 2 1s, or we could have 3 ones. So that's the number of ones. This is picking the number of parts that are equal to 1. Okay, and then we can come up with, okay, well, how many parts equal to 2 are we going to have? Well, if we could take none, we could take 1 part of size 2. We could take 2 parts of size 2. We could take 3 parts of size 2, and so on. And then the parts of size 3. Sorry, white doesn't show up on white, so I'll have to do it this way. We could have x cubed plus x to the 6th plus x to the 9th, and so on and so forth. Might as well do the last one here. I have 1 plus x to the 4th plus x to the 8th plus x to the 12th plus, and so on. And the general term, of course, that I'm getting is when I have an n by, if I want to take a part of size n, maybe I should make it a part of size m, then I just get 1 plus x to the m plus x to the 2m, and so on. So that tells me that p of x is the product for each of these parts. So we'll maybe let that be m greater than or equal to 1 of, what is this infinite series? That's just 1 over 1 minus x to the m. And that's the formula for the generating function. So I can think of it as each of these terms here is telling me which numbers I get to choose. I get to choose how many 1s, how many 2s, how many 3s, how many 4s, how many m's in general. And that's going to give me the closed form for the generating function.